Hello everyone. So welcome to class 9 of our course. So today we will be discussing what happens when a group of atoms come closer to each other. So let us first take a simple example. We have already discussed the case of a 1D potential well. So let us assume that we have two 1D potential well. So this picture basically shows the potential profile of two 1D potential wells, and this let us call or let us assume that the length of these two potential wells are basically the same, and V is equal to infinity outside this potential well, and V is equal to 0 inside this potential wells. Okay, and this is also of length L. Okay, so from what we learned in the past, quantum mechanics says that the electron should essentially be confined within this part and this part. There might be more than one electrons, but what we intend to discuss here is not about electrons but about states. So the difference between a state and an electron is that a state can exist irrespective of whether an electron is there or not. Okay, so a state can be a filled state or an empty state. So state is basically an allowed value where the electron can exist, some allowed value of energy where the electron can exist, or an allowed value of momentum wave vector where the electron can exist. Okay, so when I say that state, it is some allowed value of energy or momentum or something else where the electron can exist, but it is not necessary that the electron actually exists in that state. Okay, so as we know that in these two structures or in these two wells we have discrete states, okay, where k is basically given by, so let us say that we name these k vectors of this potential well 1 as uh, k, and here we call it as k dash. Okay, so the first state corresponds to k1, which is equal to pi divided by L. The second state of this well, that is, corresponds to k2 equal to 2 pi by L, and etc. Similarly, for this well, the first state corresponds to k dash 1 equal to pi by L. The second state corresponds to k2 dash equal to 2 pi by L, and so on. Okay. Now, when we write these two equations over here, we assume that this well and this well are basically decoupled from each other. That is, an electron cannot flow from this well to this well. An electron cannot jump from this well to this well, which is another way of saying that this distance between two wells is large enough so that the electron cannot actually tunnel through this potential barrier. Okay, so this is a thick barrier. Now let us say that we bring these two potential wells closer. Okay, so when we bring these potential wells closer, this is now separated by a thinner barrier. So now this one is basically a thinner barrier, and so an electron might be able to tunnel through this barrier and pass through to the other potential well. Okay, now how do I write the states for this structure when an electron can actually tunnel from one well to another? In quantum mechanical language, when an electron can tunnel from one well to another, or when an electron can tunnel from one atom to another, or when an electron can move from one atom to another through the intermediate space, we call that these two atoms are coupled. So here the electron can tunnel from one potential well to another, and we call these two potential wells as coupled. Okay, If you ask me from an atomic perspective, the atomic perspective is also kind of the same. So let us consider that you have two hydrogen atoms here. Okay, these are the nucleus, and then this nucleus is positively charged. So of course the potential is lower here. So if I draw a diagram for electronic potential, the electronic potential would look somewhat like this. So it is somewhat 0 far away from the hydrogen atom, and it decreases rapidly as it moves closer to the hydrogen atom. Okay, and let us draw this hydrogen atom closer. Now in the space between these two atoms, the potential increases slightly, and then as we move closer to the second hydrogen atom, the potential again decreases, and then it again increases, and it goes to 0 far away from the nucleus. Okay, so the nucleus is actually smaller in the scale of this potential, so let us call these two as the nucleus. Now this is kind of this structure, this kind of serves as potential wells, although it is not one dimensional and it is not of the form of a square, but this is kind of a potential well for the electrons. So a potential where the electron can get trapped. Now as we know that whenever we have covalent bonds, an electron can actually move from one atom to another, and if an electron can flow from here to here, these two atoms are coupled. Okay, so now how do I find the effective states in such an arrangement or in such a condition? So let us take the example of this 1D potential well first. So as I said that if the electron can move from this one structure to another, or one well from to another, these are known as coupled wells. Okay, coupled 1D potential wells. Now as I said earlier that when such a condition of coupled well actually exists, the states can no longer be given by this form, mainly because when we write this equation and this equation over here, we mainly assume that the electron wave function is 0 at this point and at this point, and here also the electron wave function is 0 at this point and at this point. If you don't remember, just revisit the potential well. Okay, and this boundary condition gives us allowed values of k states to be of this form. But right now this electron wave function does not go to 0 at this point or at this point, because the electron can tunnel or can pass through this structure. So if the electron can pass through this structure, it basically means that the electron wave function must have a finite value somewhere here or somewhere here. Okay, otherwise the electron cannot move from one well to another if it goes to 0. Okay. Okay, so now how do we find the allowed k states in such a structure? So now let us consider the extreme case that if this barrier, if we bring these two wells closer to one another, and if we continuously keep on bringing these two wells close to one another, one time the barrier would basically reduce to 0. Okay, if we keep on reducing the thickness of the barrier gradually, so a time would come when the thickness of the barrier would become 0, and then we would have only a single potential well. So here I have basically drawn such a structure where I have basically brought this well and this well so much close to one another that I have reduced this barrier thickness to 0. Okay, so the two wells are joined now, and this length is basically 2L, and again as before v equal to 0 inside and v is equal to infinity outside this well. So now I have made this barrier thinner and joined these two wells. I have a single well of length 2L, and now the k states are not the same as this set or as this set, but the k states entirely evolve to give us a new set of k states. Okay, so now the k states can be written as k double dash equal to, the first state is k double dash 1 equal to pi by 2l, the second state k2 double dash is equal to pi by l, and so on. So the key point that you take away from here is that whenever you bring two potential wells or two atoms or two structures closer to each other such that the electrons present in each of those two structures can flow from one structure to another, or the electrons present in these two structures or in these two atoms can interact with one another, then the electronic states completely evolve or completely mix up to give rise to new states, and this phenomena is known as coupling. Okay, this is the same situation which arises when you bring a chain of infinite number of atoms together. Okay, so when you bring a chain of infinite number of atoms together, for example in case of bulk silicon where a number of atoms are arranged in a crystalline fashion, the orbitals mix up to form energy bands. Okay, so the orbitals that were discrete in energy before now mix up and give rise to new set of energy levels which we call bands, because the energy spacing between two states now is really very small. Okay, so the same situation arises in this case also. Now here we would basically, as an example, we would take two atoms and hypothetical ones, simple and hypothetical. Let us consider hydrogen atom which contains two, not hydrogen atom, but let us consider an atom which has only one electron or only one state. Okay, again this is entirely hypothetical situation, but this would give you a sense of how to do the computation. Of course, when you do a computation or when you write a code to compute things for larger structure, you need to use a computer because you cannot do it by hand. Things are very complicated, but the method is basically the same, and my intention here is actually to highlight the method or to give you a sense of what coupling is and how it gives rise to new set of energy levels or new set of allowed states. Okay, so we have two atoms and we are assuming that we only have one state per atom. Okay, initially these atoms were far apart, and as I said that each of these atoms have only one state. That's an assumption that we are making here, and we will also assume that we know information about the state of the atom, about the initial state or initial orbital of the atom. Okay, and as you know that in quantum mechanics language each of these states are known as orbitals, and we'll assume that we have solved the wave function for this orbital of this atom. So this is the let me delete this part. So this is the initial condition that this is one atom, this is another atom which is far apart, and the orbital of the atom looks somewhat like this. This is again an assumption that we are making. Okay, this is 1, or let us call it L and let us call it R. L for left and R for right. Okay, we have solved this orbital. This orbital we call it UL and this orbital we call it UR. Okay, so we know the energy of this orbital, which is E1, and E1 UL is equal to minus h square by 2m del square plus u nr ul. Okay, so this is the potential created by the nucleus, or the potential energy created by the nucleus. This un corresponds to the potential energy created by the nucleus of this left atom over here. Okay, and this entire thing is known as the Hamiltonian of the system. this is H, we will call it HL, L for left. And similarly for this atom also we have a similar situation. We call it E1 mu r equal to again minus a square by 2m delta square plus u, let us call it n dash r mu r, and this again is the Hamiltonian of the right system, which we call as HR. Now this un dash and this un have the same form because the atoms are the same, but it's just that they are separated in space, that's it. Okay, but the form is basically the same. Now these two atoms are basically brought closer to each other. So these two atoms are brought closer to each other. Let me write it at the corner over here. And so their orbitals are basically overlapping. Okay, same we have mu L, mu R. This is atom number 1, this is atom number 2, and the potential for this nucleus is given by UNR, and the potential for this nucleus is now given by UNR, UN dash R. Okay. Now of course again UNR and UN dash R are basically the same, but the only thing is that their spatial dependence is different. Okay. Okay. Now the Hamiltonian of this entire system, what is it? The Hamiltonian of the entire system is now minus h cut square by 2m delta square plus un r plus u n dash r. Okay, because the electron present in this orbital is also going to feel the repulsion due to this nucleus 2 over here. Okay, so that is why the Hamiltonian of the entire system is given by this form. And similarly the this electron in this orbital over here is also going to feel the not repulsion but the attraction due to this nucleus. Okay, the interaction is present. Okay, so the total Hamiltonian is given by this kinetic energy term, and the potential energy term is given by this form. Okay, now we do not know what is the total wave function of the system or what is the total wave function corresponding to an eigen state of the system. And because this orbital, two orbitals have overlapped and the overlap lies somewhere around here, electron from this state UL can readily flow into the other state UR. Okay, electron from this state can readily flow to this state through this overlap around here. Okay, and this is how electrons flow in a crystal, that the atoms are arranged periodically, and the orbitals basically overlap with one another, and this overlap of orbitals basically creates covalent bonds, and through these bonds, it is through these bonds the electrons would actually flow. Okay, so now we have this two orbitals UL and UR, which we have solved in advance, and we know that the total wave function corresponding to an eigenstate of the entire system must be given by an overlap of these orbitals. Okay, it is not that the total wave function should not have the properties of the orbitals, but it is actually given by an overlap of these orbitals. Now how the orbitals will overlap, that is up to the system, but it would be given by the overlap of the orbitals. It is the constituent orbitals that make up the eigenstate of the system when the atoms are brought closer to one another. Okay, this is known as linear combination of atomic orbitals. So let me write it here. LCAO, and this basically means that when atoms, when orbitals of different atoms interact with one another, the eigenstate of the entire system can be expressed as a linear superposition of the constituent orbitals. Okay, which is to say that an eigenstate of the entire system psi can be expressed as a linear combination of the two orbitals. So we have this coefficient phi L and phi R. Okay, so this is the eigenstate of the entire system. This is the eigenstate of the system when the two atoms were far away from each other. That is, this is the eigenstate of the isolated atom. Okay, the orbital of the isolated atom. Okay, so in an isolated atom, you already know that we have different orbitals like 1s, 2s, 2p, then 3s, 3p, 3d. Then there are 4s, 4p, 4d, 4f. So like that. Okay, each of these 1s, 2s, etc. These are the eigenstates of the isolated atom. Okay. So I again repeat that this is the eigenstate of the entire system when the two atoms are brought closer to each other, and this one and this one are the eigenstate of the isolated atom. Now, because these two atoms are the same, the eigenstates of the isolated atoms are also the same. The only thing is that their spatial dependence is different because they are basically separated in space by some distance. Okay. Okay. Other than that, the shape or the form of this eigenstate of the isolated atom or the orbital are basically the same. Okay. So our eigenstate is given by psi L u L R plus psi R u R, sorry, phi R u R R. Okay. Now, since this is an eigenstate of our entire system, it must satisfy the Schrodinger's equation. And how do I find this eigenstate or eigenwave function? So our basic job should be to calculate this phi L over here and phi R over here. If we know what is the value of phi L and phi R, or if we know the relative ratio of phi L and phi R, then we can actually know this wave function or the eigenfunction psi R. Okay, so our purpose here is actually to calculate the value of phi L and phi R. Okay. Okay. So now, since this is an eigenfunction of the entire system, this must satisfy the Schrodinger's equation, and we assume that the eigenenergy of the entire system is E. So E psi R is equal to the total Hamiltonian. So the Hamiltonian is an operator. psi r, which is equal to minus h bar square by 2m delta square plus u n r plus u n dash r psi r. Okay, so this is Schrodinger's equation. Now how do we proceed from here? So what we do is we just multiply this psi r, or we multiply the entire equation by first ULR and integrate. So when I say integrate, this integration basically extends over all space. So since atoms live in three-dimensional space, the integration is over volume. So I am not writing three integrals to denote three dimensions of the coordinate, that is x, y and z. So I am just writing as an integral, but when I write integral over here, it basically means the integration over volume. Okay, so I multiply and integrate ULR E psi r dr is equal to integral ULR, then the Hamiltonian minus h cut square by 2m delta square plus un r plus un dash r and multiplied by psi r, but psi r is basically equal to phi l ULR plus phi r URR. Okay, now note that this is the Hamiltonian of the left isolated atom, which we discussed previously. So let me go back to that page. So this was the Hamiltonian of the left isolated atom, and this is the Hamiltonian of the right isolated atom. And this Hamiltonian when operated, this Hamiltonian when operates on this orbital UL gives us the eigen energy E1 times UL. Okay, we should actually write a special dependence over here, which I forgotten. Okay, so this part is basically our HL. Okay, so this I can just write this part. Here E is a constant, so E comes out of the picture. So UL E integral of, we have a dr over here, ULR psi r dr, this is equal to integral of ULR, then this part was the Hamiltonian of the left isolated atom, so minus h cut square by 2m delta square plus UNR ULR dr, okay, plus integral of ULR U n dash r ULR dr plus integral of we have a phi l over here, actually phi l, here also we have a phi l because of this phi l over here, plus integral of plus phi r integral of UL, then note that this part is basically the Hamiltonian of the right isolated atom. Okay, I again am going back to the previous page. So this part is the Hamiltonian of the right isolated atom. Okay, so we write it here. that you have a r dependence over here, then minus h bar square by 2m delta square plus un dash r, let me write in a smaller font so that it's plus phi r integral of ulr minus h bar square by 2m delta square plus un dash r, then u r r dr. Okay, this is the Hamiltonian of the right isolated atom, plus integral of plus phi r integral of ulr. Actually we multiply it with the complex conjugate over here, so I'll just correct it, but let me complete this statement. unr urr dr. So we multiply it with the complex conjugate over here because that is what we use to normalize things. Why we multiply it by the complex conjugate will become clear in a moment. Okay. Now here I have pasted the equation from the previous page. Now let us first understand what this term is. So let us go back to a fresh page. So integral of ul star r psi r is basically equal to integral of ul star r phi l ul r plus phi r sorry u r r dr. We should have a dr over here. So which is basically equal to phi l integral of ul star r ul r dr plus phi r integral of ul r urr dr. Okay, now this is the integral, this is the inner product of the orbital wave function of the left isolated atom. So since this must be normalized, this integral should be equal to 1. So this is equal to phi l, and this one basically depends on the overlap of the orbitals of two atoms. Okay, so here the wave functions are basically overlapping. Okay, at all other places, for example somewhere here ul has a definite value but ur is basically 0, so the product is 0. Here at this point also ul is 0 but ur has a definite value, so the product is again 0. So it is only in this region that both ul and ur have some finite value. So the integral, the value of the integral comes from here, because only in this region the product is non-zero. So how much the integral value is, or what is the value of the integral, this basically depends on how much overlap there is between these two orbitals. Okay, so we have phi l plus, we denote this integral by the term s, plus phi r times s. Okay, there should be a complex conjugate over here. So s is nothing but s is equal to integral of ul star r u r r dr, which is equal to integral of u r r star u l r dr. Now why this two should be equal, this can be understood intuitively, because if I flip the system from around the midpoint, so this is the axis and the system is symmetrical about this axis to the right and to the left. If I flip this system around this axis, there is no way of knowing that whether I have flipped the system or not. Okay, so if I flip, this is another way of saying that if I flip this L and R in this equation, I will have basically the same result. Okay, that's the intuitive way of understanding this. Okay. Okay. So this is this left term is basically nothing but this is equal to phi L plus S phi R. This is equal to, now this part, just as I said, is the Hamiltonian of the left isolated atom. So this entire thing is equal to E1 times ULR, just as we noted in the previous page, that this entire part is equal to E1 times ULR. Okay, so let's go back to the original page. So this is equal to phi L integral of phi L. E1 is basically a constant, so E1 would come out of the integral UL star R ULR dr. Okay, now this term over here, this term is again E1 times UR. Okay, plus, so the third term is phi R. E1 is a constant, so E1 comes out of the integral. So integral of UL star R URR dr. So this is the third term. Let me just denote it by an arrow here, which term comes from where. So this first integral basically gives rise to this term. This third integral gives rise to this term. Now the second and the fourth are left, and the second and for the second and fourth term, so we call this integral, again it's not possible to calculate the value here because we are not really dealing with a specific shape of an orbital, or we do not know the shape of the potential here, the potential function, that is, or the orbital function, but we are just working in terms of symbolic terms. So we will denote this kind of integral by a letter. So let me write it here. Let's go to a new page. So we'll call the second term or we'll denote the second term by the letter A. This is equal to integral of UL star R UN dash R UL R dr. Okay, and due to the symmetry of the system, again, because if I flip the system around the mid axis, there is no way of knowing if I have actually flipped the system or not, because it is symmetrical. So this by symmetry is equal to integral of UR star R UN dash UN over here UNR UR R dr. Okay, so we denote this kind of terms by this letter A, and so this is basically our A over here, and we have a multiplied it by phi L, so plus phi L A. Okay, and again I denote this by an arrow that this has come from, let me change the color. So this third term gives rise to this term over here, and then we have this fourth term, this one, and again we denote this kind of integral by a symbolic term. So let us call this as B. So B is equal to integral UL star R UNR UR r dr, and due to the symmetry of the system, this is equal to integral of u r star r u n r u l r dr. This is equal to u l r u l star r u n r u r r dr. Actually this should be equal to u n dash. This is equal to integral of u r r u n dash r u l r dr. Okay, so we'll denote this kind of terms by this letter b over here. So plus phi r into b. So this term basically, again let me draw an arrow over here. So it basically comes from this term over here. Okay, so now we have got an entire equation, of course in symbolic terms. So let me write the entire equation here. So phi L plus S phi r. So the entire equation is phi L plus S phi r equals to, we go back to the previous page. So this integral is basically 1 because the orbitals are normalized. This integral is again basically S, the overlap integral that we defined earlier. So phi L, okay, so let me write this entire equation over here. Phi L E1 plus phi L A plus phi r S plus phi r b. So phi r S plus phi r b. So which is equal to phi L E1 plus A plus phi r S plus b. Okay, so this is our entire equation that we have got on integrating things. Actually this is E1S actually, which I forgot to write. So this is basically E1S plus b. Note that in arriving at that equation, we have basically multiplied this both the sides of this equation by ULR, and we have integrated it. Okay, both sides we have integrated. Now if we actually multiply both sides of this equation by UR, if we multiply it by UR and integrate, then we will actually get a different equation. So you can practice it, or you can derive it yourself. So I am just writing the result over here because it is tedious to do the same thing again, but I hope that you understand the method how we arrived at this equation is also how we can actually arrive at the second equation. You multiply both sides by UR instead of UL and integrate both of these sides. Okay, so this is the first equation. Now if we multiply with both the sides of that Schrodinger's equation by UR and integrate, we will arrive at a second equation which kind of looks this is we have an E over here actually, which we forgot to write. So we have an E over here because this E was present here. So let me write it. There should be an E over here. Okay, this E corresponds to the eigenenergy of the system. So let me change the color. E. So if we multiply the entire Schrodinger's equation by UR and integrate, we will just arrive at a second equation, E S psi L. Because the system is actually symmetrical, we can readily arrive at the second equation, or we can write the second equation by replacing this L with R and this R with L in both sides of the equation. Okay, because the system is basically symmetrical about the mid axis. Okay, so plus psi R, this is basically equal to phi L E1 S plus B. So we replace this R by L and we replace this L by R, plus phi R E1 plus A. Okay, so now we have two variables to solve, which is phi L and phi R, and we have two equations. So we can, if we have two equations and two variables, we can readily solve these two equations if the equations are not dependent set of equations. So we can write it in matrix format. So E 1 is, so here we would write this variable phi L and phi R. 1 is S1. So this is the first equation. This the coefficient of phi L is 1, the coefficient of phi R is S. So I do hope that you know how to write these two equations in matrix format, so I am not discussing it here. Then this E1 plus A, E1S plus B, E1 S plus B, E1 plus A, phi L and phi R. Okay, so we can basically solve this equation. This is again the entire thing reduces to an eigenvalue and eigen vector problem. So we can just write E phi L phi R equals to 1 S1 inverse E1 plus A, E1 S plus B, E1 S plus B, E1 plus A into phi L and phi R. Okay, so I am not going to solve this eigenvector and eigenvalues for this equation. You can actually readily do it in MATLAB. In MATLAB there is this Sims toolbox or Sims command which takes equations in symbolic form and basically solves it for you. So you can try that if you want to solve it yourself. So I am just writing the result over here. The two eigenvectors. So let me write it: eigenvectors and eigenvalues. So this is the eigenvalue of this matrix equation. So the two eigenvectors are phi L phi R equals to 1 1, and the corresponding eigenvalue is E1 plus A plus B divided by 1 plus S. Okay, we call this bonding orbital or bonding eigenstate, and the second eigenstate, which we call the antibonding eigenstate, is basically 1 minus 1, and the corresponding eigenenergy is E1 plus A minus B divided by 1 minus S. We would not go into discussing the detail of what are the corresponding relative values of A, B and S, but for this class, just know that this bonding energy is generally lesser than anti-bonding energy, and that is why whenever two atoms actually come closer to each other, the electrons actually exist or reside in this bonding orbital actually. Okay, and then let us write the wave function of the bonding and the anti-bonding orbitals. So as we can see, the coefficient of this bonding orbital are 1 1, and the coefficients of this anti-bonding orbital are 1 and -1. Okay, so the wave function corresponding to the bonding orbital is basically phi L r plus phi r r, and then it should be normalized because the integral of this wave function with its complex conjugate, okay, so if we multiply it by the complex conjugate and integrate over all space, the integral should be 1. So if this should be normalized, so we can actually basically write this normalization constant over here. I think it should be 1 by root 2, but I am not sure, so I am writing it as 1 by z, where z is the normalization constant. And earlier, when we started, we said that these are the two atoms, and their orbitals basically are overlapping like this. So if we sum up these two orbitals, what we get from here, the structure is basically we have these two atoms, and then this is 0 far away rises, and at the overlap region it is higher than before, and it then gradually deteriorates. And this high antibonding no, this actually should not be 1 by root 2 actually, and it has to be calculated because there is overlap between these two orbitals. If there would be no overlap, then this would have been 1 by root 2, but here since there is overlap, it would not be 1 by root 2 actually. Okay, so this is again, let us write this constant as za, and this is 1 by zb, where again zb is a normalization constant. So this is psi lr minus sorry, I am writing it in the wrong format. So this is a ul actually, ulr plus urr, and this is equal to ulr minus urr, and so this would kind of look like this. So we have two atoms again, and we are subtracting one wave function from another, so this is kind of a destructive interference. So at the overlap region, this region, the wave function or the electron density should be lower, and exactly at this point it should be 0. Okay, so this rises, and then it becomes 0 somewhere here, then it becomes negative, and then it decays. Okay, now here one of the reasons why the energy of this antibonding orbital is higher from an intuitive perspective is because here most of the electron density is actually located here and here, so there would be electron-electron repulsion. Although we have not actually included electron-electron repulsion in this picture, okay, to simplify things basically, but electron-electron repulsion is actually present, and the electron wave function is lower around here, which means more electron is concentrated closer to the atom. So the electron-electron repulsion is higher, and the second reason is because earlier we had this electron concentration between these two atoms, and both these nucleus are positively charged, so they repel each other. Now if an electron density is present between the atoms, it basically screens the positive charge of the nucleus, so the nuclear repulsion becomes lower in the bonding orbital, in the antibonding orbital, in between the atoms, the electron density is very low. Okay, it is 0 here, but here also it is lower actually. Okay. Now, because the nucleus is almost unscreened in this case, or screened by a lower amount in this case, the nuclear repulsion is higher, and that is why the nuclear repulsion is higher. So this basically increases the energy of the entire system. Okay, so let us do up to here today. One thing I would like to state, and which you should also know, is that this Hamiltonian that we considered in this case is pretty straightforward. It is basically the kinetic energy term plus the repulsion due to the the attraction between the two nucleus. Sorry, not between the two nucleus, but the attraction between the electrons and this right nucleus and the electron and the left nucleus over here. In reality, we should actually include other terms as well. One is the nuclear repulsion. So the actual Hamiltonian basically would look like this. Plus u n dash, which is the nuclear repulsion. So this is basically the nuclear repulsion or repulsion between two nucleus, plus the repulsion between the two electrons. Okay. Now, in most of the cases, we will not go into detail of this, but in most of the cases, this is the exact term that makes this entire Hamiltonian unsolvable, because this involves a self consistency, because the electrons are basically spread in the spread along the entire orbital or spread throughout the space. Now, to know the exact wave function or to know the eigenstate, we need to know this form. What is the mathematical form of this term? Now, the mathematical form of this term depends on the eigenstate. Okay, so there is a self consistency involved. So even in very simple systems like helium or hydrogen, okay, if you are considering hydrogen molecule, then even then it is not possible to solve the Hamiltonian or the eigenstates of the system by hand, because we do not know this form. Okay, to know this form, I need to know the eigenstates of the system. To know the eigenstates of the system, we need to know this form. Okay, so this involves a self consistency which which makes it difficult or almost impossible to solve by hand, and so we have to resort to a computer. Even for a computer, it is very difficult to solve things. Okay, things are so much complicated here. It might not be obvious to you at this moment, but if you go, if you want to do research in this field, then things would become clear later. But right now, just know that it is this term which makes the Hamiltonian unsolvable, and we really have to resort to various level of approximation and other things to solve this Hamiltonian or solve the eigenstates and eigenenergy of the system approximately. Okay, and even with this approximation, it is very difficult for the computer to solve, and we really need very high power computers to actually solve these systems. Okay, and this term this term or the self consistency involved in this term has given rise to an entire theory, which is known as density functional theory or DFT. Okay, so this is the electron repulsion term. Okay, so let us do up to here today. I hope you have got an idea that whenever two atoms come closer to each other, how the states basically mix up to give rise to new states. And this is also exactly how you would solve a system with 3 atoms, 4 atoms, and with a system with n number of atoms. This is a generalized method, but the things are same when you actually when you actually want to solve, let us say, a system of silicon crystal or germanium crystal. Okay, so this is a generalized method, and I hope that you have got a an approximate idea that how do states evolve when you actually bring isolated atoms closer to each other, or when the electronic wave function start to interact with each other. Okay, okay, thank you.